Hey guys, welcome back to another science adventure. Today, we're going to say
hello to my little friend!
Let's get started. So today's experiment was inspired in part by a video over on the Backyard Scientist channel. And he did a video where he made a cannon kind of similar to this. It also used propane and he shot golf balls out of it.
It's really loud. This thing could shoot a golf ball farther than you can see with your eyes. If you'd like to make one of these yourselves, I've included the plans I made for the cannon down below in the video description.
And I was like, hey, that's pretty cool. But there's something I want to know, which is, does the barrel length affect how fast the projectile gets shot out? So that's what we're going to test today. So I went ahead and I designed a pretty simple cannon. It's just a piece of vinyl tube connected to a large PVC pipe, which serves as the combustion chamber. It's all epoxied together here and here. And then I've got an adapter, which is here. That's also epoxied on, and then I've got a little metal clip that I just made out of a piece of wire, and that holds on the barrel, so that way I can swap the barrel on and off as I choose. And you can see here I've made marks at 6-inch increments along this barrel. So the idea is that I'm going to load the cannon up, fire it a few times for consistency, then I'm going to cut off 6 inches, and then I'm going to repeat the experiment, cut off 6 inches, repeat the experiment, and we're going to gather some data and see what it looks like. So as with all proper experiments, the first thing we do after we raise a question is we think about a hypothesis. What do we think is going to happen when we test it? So what I thought was going to happen was we were going to find that as you decrease the barrel length, you'll also decrease the velocity. But I also thought that if you increase the barrel length, you'd be able to increase the exit velocity up to a certain point, and then it would start to decrease again. So I'm going to make a couple parts to my hypothesis. I think, number one, that yes, barrel length is going to affect the velocity at which the projectile goes out the end of the barrel. I think also we're going to see that when you decrease the barrel length, you're also going to decrease the velocity. And here's why. I think that when you have the propane in here and you fire it, it's going to start to push it along. And then when it's still inside the barrel, you're going to confine that gas, and the only way it's going to get out is by pushing the projectile along. So that's why it's going to accelerate when it's inside the barrel. Once you get out the end of the barrel, here, your projectile comes out the end and the gas is free to expand everywhere, and it no longer pushes the projectile along. So that's why I think if you decrease this, you'll decrease the amount of time the gas spends pushing the projectile along, and you're going to decrease that velocity when it exits the barrel. So I'm going to go through the method that I use to calculate the velocity. So the method is the same for every single trial. Here's how we do it. First of all, I'm going to load it into Windows Movie Maker. You can see here I've just opened the preview frame to be as wide as I can, and we're just going to start counting frames. You can count frames with L and J. They move forwards and backwards by individual frames. So we're going to look at the end of the cannon there, and I'm going to press L, 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 L. Where is it going to come out? There we go. So you can see it came out right there. So that's the first frame it spent in the air. You see right there. So we're going to start counting. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you can see 17 and then 18 is where the impact occurs. So we're going to call that 17 frames spent in the air because it collided on the 18th frame. Alright, here's our distance to the target. If it wants to focus there, we're at 22 feet and 5 inches. Alright, so here's how we do it. We say 17 frames times 200, or we're going to put that, right, we're going to say there was 1 second of recording in real life equals 240 frames captured. So that means we spent 0.0708 seconds in the air. Alright, now remember, speed is distance over time, so our distance was 22 feet and 5 inches. I'm a little bit slow because I'm trying to use my calculator through the viewfinder. And our time was what we got before. I'm going to press enter and we get 316.47 feet per second. So now all we got to do is go over here, calculate feet per second to miles an hour, right? So we got 316 0.47. And that gives us a speed of 215 miles an hour. So while we look at this time-lapse footage of me analyzing all the data, I want to take a moment to talk about the sources of error, because that's a really, really big part of any experiment. I tried to minimize the sources of error in this experiment, mainly by using cinder blocks and bricks to keep the cannon steady while it was firing, and using the same barrel and the same projectile every time to ensure that the friction inside the barrel and the projectile velocity are not affected. However, there was some stuff I could not really control. For example, if you look at the ideal gas hull, you'll see there's some parameters that I have to try to keep consistent in order to make sure that the propane exerts the same force on the projectile every single time. Also, I don't think the propane completely burns, and I don't think it burns to the same level of completion every single trial. So those are both sources of error that you're going to have to keep in mind when you're doing this experiment. Also, you'll see in some of the shots that the projectile wobbles around in the air, and in one of them it actually bounces off the ground before hitting the target. So that's also going to be a big factor in measuring the velocity of these projectiles. Overall, I think these sources of error were able to be minimized by the use of multiple trials, and I think if I performed more trials, I would have had even better data. So you can see here for yourself that the results show I was at least partially correct. Decreasing the barrel length does actually decrease the velocity of the projectile. However, it seems that the curve is upside down compared to what I'd predicted before, so I might have to redo this experiment with data points farther apart and see how that affects the trend and if I get any better results. Anyways, I think this experiment was a success, and I hope you enjoy the video. Thanks for watching. Why is it so windy all the time? I'm trying to film.
3, 2, 1.
Really? Really? It's April now. Why is there snow? So it seems that using a tarp to catch the projectile after it's come out of the cannon is not really a viable option, because you see this is where the projectile came in, and it went through this layer, went through this layer, and this layer, and it kind of stopped right there. You can see it like in the spot where it embedded itself. It's still kind of in the shape of the projectile. You can see it kind of stuck itself in like that, with this end kind of stuck in here, and then it kind of bulged this side a little bit. Let's see, you've got some shreds of tarp, so I'm gonna have to find a different way, I guess.